Ever look at the winding path of a roller coaster and think, how on earth would you measure its exact length? I mean, you can't just use a ruler, right? Well, today we're going to pull back the curtain and unlock the calculus behind measuring any curve in space. We are diving deep into arc length. So here's our game plan. We'll start with a basic idea of what it even means to measure a curve. Then we'll get our hands on the actual formula. After that, we'll walk through a real example step by step, touch on a slightly more advanced idea called reparameterization, and then wrap it all up with the key things you need to remember. Sound good? Let's get into it. All right, let's start with the big picture. Before we throw any formulas at you, let's just think about the problem. How should we approach measuring something that's constantly twisting and turning? Let's build up some intuition first. So look at this, it's all over the place. A straight ruler would just connect the start and end points and miss all the details. So what's the calculus way of thinking? Well, like with so many things in calculus, the secret is to break a big, complicated problem into an infinite number of tiny, simple pieces. What if we could chop this curve into millions of teeny tiny segments that are almost straight, and then just add them all up? And this slide right here, this is the whole secret. We all know this basic formula from like middle school physics. Distance equals speed times time, right? If you're going 60 miles an hour for 2 hours, you've gone 120 miles. Simple. Well, arc length is just the grown-up calculus version of that same idea. Integration is just a fancy way of adding things up. So we are literally just adding up the little bits of distance you cover in every tiny moment of time. Okay, so now that we have the core concept down, that we're just summing up speed over time, let's look at the actual mathematical tool that makes it all happen. And here it is. L is for length, obviously. The integral sign just means sum up all the pieces from a starting time A to an ending time B. But the most important part is what's inside, that r prime of t. It looks a little intimidating, but all it means is the magnitude of the velocity vector. And guess what? The magnitude of velocity is just a fancy term for speed. So this formula literally just says length is the integral of speed. That's it. Now, when we break it down into the x, y, and z components, it looks like this monster. But don't let it scare you. I promise this is just the Pythagorean theorem in 3D. All we're doing is taking the speed in the x direction, squaring it, adding it to the speed in the y direction squared and the speed in the z direction squared, and then taking the square root of the whole thing. It's just how you find the total overall speed at any given instant. All right, theory's great. But let's actually see how this works in practice. Let's get our hands dirty with a classic example to make this all feel a lot more real. Okay, so we're going to find the length of one full rotation of a helix. You can picture it like a spring or a spiral staircase. It's described by this vector function, and we want to know the length as our time parameter t goes from 0 all the way to 2 pi. Step 1 is always the same. You have the position, so you need to find the velocity. And how do we do that? We take the derivative. The derivative of cosine t is negative sine t, the derivative of sine t is cosine t, and the derivative of good old t is just 1. Easy enough. Okay, next up, we need the speed. That means finding the magnitude of that velocity vector we just found. So we square each component, add them all up, and stick them under a square root. That gives us sine squared t plus cosine squared t plus 1 squared. And right here is where a little bit of magic happens. You see that sine squared t plus cosine squared t? You gotta remember this from your trig class. That is one of the most important identities. It's always equal to 1, no matter what t is. And that is a total lifesaver here, because it makes our expression so much simpler. Our speed is just the square root of 1 plus 1, which is the square root of 2. It's a constant. The speed never changes. And finally, the last step, integrate. We integrate our speed, which is just the constant root 2, from our start time, 0, to our end time, 2 pi. And integrating a constant is the easiest thing in the world. We get the square root of 2 times t, plug in the numbers, and bam, our final answer is 2 pi times the square root of 2. That is the exact, precise length of one loop of our spiral. Okay, so we've totally mastered the basic process. Now, let's just peek at a slightly more advanced idea, but it's an incredibly powerful way of thinking. It's all about shifting our perspective from time to distance. This is called reparameterization. Think of it this way. Normally, we say, where is the car after 5 minutes? We're using time, t. With reparameterization, we ask a different question. Where is the car after it has driven 5 miles? We're describing its position based on the distance it's actually traveled along the road. We're going to call that distance s. We're swapping t for s. And this slide lays out that shift perfectly. On the left, with RT, your position depends on what the clock says. On the right, with RS, your position depends on what your car's odometer says. It's a much more natural way to describe the geometry of the path itself, without caring about how fast you were going. So, how do you actually do it? Well, it's a three-step process. Let's use a circle as an example. First, you find the arc length function s of t, which for this circle turns out to be just 3t. Second, you do a little algebra to flip that equation around and solve for t, so t equals s over 3. And finally, step 3. You take that expression for t and plug it back into your original position vector. And voila! This is what you end up with. Your new position vector is a function of s, the actual distance you've walked along the edge of the circle. So if you want to know where you are after you've traveled, say, 5 feet along the circumference, you just plug s equals 5 into this formula. It's incredibly direct. All right, that was a lot. We've covered a ton of ground here. So let's zoom out and boil it all down to the absolute essential things you've got to take away from this. Okay, here it is. If you forget everything else, remember this. The core idea is that arc length is just the integral of speed. It's just distance equals speed times time in calculus form. The key formula you'll use is the integral of the magnitude of r prime of t. And the process is always a simple three-step dance. Differentiate to get velocity, find the magnitude to get speed, and then integrate to get the final length. Differentiate, magnitude, integrate. That's the mantra. So, there you have it. You now have this incredibly powerful tool in your math toolbox. You can literally calculate the length of pretty much any smooth curve you can write an equation for. Think about it. What does that open up? The flight path of a satellite? The exact length of a strand of DNA? The real-world paths you can finally measure are kind of mind-blowing. Thanks for watching.